السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين. So please don't forget to make the attendance online. Don't forget to make the attendance online. So we go to complete our classes. So here we have algorithm design technique, the brute force. We have here introduction to brute force. We have selection sort and bubble sort, sequential search and string matching, closest pair problem, exhaustive search, traveling salesman problem, knapsack problem, assignment problem. What is the defining of brute force? Brute force is a straightforward approach to solving a problem, usually based on a problem statement and definitions. Some example here, computing an a greater than 0, n is a non-negative integer. Computing n factorial, multiply 2 n by n matrices, and selection sort, and sequential search. So important algorithm design strategy, brute force, we have applicable to very wide variety problems. For some important problems, we have sorting, searching, matrix multiplication, string matching. Brute force approach yields reasonable algorithm for at least some practical value with no limitation on instance size. The expense of designing a more efficient algorithm may be unjustifiable if only a few instances of problem need to be solved. Brute force can solve those instances with acceptable speed. In general, brute force is efficient, but it is still useful in solving small-sized instances of problems. Can serve an important theoretical or educational purpose. So here we have brute force ideas for some problems. Here is sorting. Find the whole array that correct elements at each index. Searching, check key element at every index. A geometry problem, closest pair, means compare all the pairs of point distances. Graph, here shortest path. Search set of edges based on the correct source node to destination node with minimum total weight in graph by trying all possible paths. Minimal spanning tree, select n minus 1 edges where n is number of vertices that will connect all vertices with minimum total weight. Traveling salesman problem, TVP, or something TSB, means traveling salesman problem. Travel from source node to all other nodes exactly once and return back to source code with shortest path by returning all possible node arrangement. And combinatorial problem, knapsack, select a set of items which is specified with weight and value with total weight equal to or less than some constraint weight with maximum total value by trying all possible set of items. Here we have brute force strength and weaknesses. So here wide applicability for brute force is wide applicability simplicity and yields reasonable algorithm for some important problems, example matrix, multiplication, sorting, searching, string matching. Weakness point of brute force rarely yields efficient algorithm. Some algorithms are slow. Need to try all possible solution. So here we have to try all possible solution. Brute force. Let's assume we have this sorting algorithm. So here we have here we have how many times we solve this one. We solve this one. I think we have error in this algorithm when you open this one. Okay, it is n power 2 minus n divided by 2. Okay, here I have complexity is theta n2 on all point inputs for number of key swaps. Okay. So here scan the entire list, find smallest element, exchange it with the first element, putting the this is the selection sort, not bubble sort, selection sort. So here we have entire the smallest element, exchange it with the first element, putting the smallest element in the final position in the sorted list. Scan the list starting with the second element, find the smallest, and here exchange exchange it with the second element, putting the second smallest element, and we do this one. On the ith pass through to the list from 0 to n minus 2. Here from I plus 1, I plus 1 to j I plus 1 to n minus 2. The algorithm searches for the smallest item among the last n minus 1 element and swap with A. After n minus passes, the list is sorted. We have this example that we did last week. Okay. We go for sorting algorithm bubble sort. To compare adjacent element of the list, exchange them if they are out of order. Okay. To compare adjacent element of the list and exchange them if the array if they are out of order, swapping until the largest element is at the last position of the list. Okay. So bubble sort, we compare here algorithm bubble sort, an array 0 to n minus 1. The output is sorted array for I 0 to n minus 2, for j I here from 0 to n minus 2 minus I, or here from j plus I to j from I to n minus 2, and I plus 1, I plus 1 to n minus 2. Here we have this one. Okay. So here we have n minus 1 multiplied n divided by 2. The number of key, however, depends on the input. In the worst case of designing arrays, it is the same as the number of key comparisons. First two classes of Google sort on the list is 89, 68, 90, 29, 34, 17. A new line is shown after a swap of two elements is done here. So we compare this one with the elements and we replace this with the this point. We compare this with the rest and like this. Okay. Sequential search. Here we compare successive elements of a given list with the given search key until either a match is found, successful search, or the list is exhausted without finding a match, unsuccessful search. Finding a match or unsuccessful search. Here, best case is the item being searched is the first element in this list of 0. So here we have O1. Item being searched here element is O1. Worst case, the item is being searched in the last element list ON. So here, if we have best case, we will have the key at the first point of the array. However, for key worst case, the item being searched is the last element in ON. Okay, so if I give you sequential set or bubble sort, I told you study the worst case and the worst case and best case, and you have to give me the formulas and write the what is the best solution for best case and worst case, or sequential search or bubble sort or for all of them. Okay, closest pair program. Here, as I told you, we have a point, okay, and we have another point. We have many points. We want to check which pair are closest pair. So here we find the two closest points in a set of n points in two-dimensional Cartesian plane. Find the two closest points in the set points in the two-dimensional Cartesian plane. Okay, brute force compute the distance between every pair of distinct points and return the index of the points for which the distance is smallest. So here you will compare the distance between every pair of distinct points and return the index to the of the points of which the distance is smallest. Here, for simplicity, we'll consider the two-dimensional case of the closest pair probability. We assume that the points in question are specified in a standard fashion by the XY Cartesian coordinates and that the distance between 2 points PIXY, YIXI, PYY, and PJXJ, and is the standard Euclidean distance here. So here PI, here AX minus 1 power 2 and plus YI minus 2 power 2. Here we get the distance from P and Q. Algorithm, brute force closest pair point. Here find the distance between closest pair here. So find distance between the two closest points in the plane by brute force. A list of P of n greater than 2 points pxy until peaks n. Output the distance between the closest pair points, d equal infinity. So here we have for I equal to 1 to n minus 1 do, for j equal to I plus 1 do, d 9 here minimum SQRT here means we know SQRT d and SQRT xy. So here we compare between d and SQRT xi minus xj power 2. If this one SQRT is bigger than d, we'll take d. If this one is larger than d, if this one is less than d, we'll use this one. Return d. The basic operation of the algorithm will be squarting a number. The number of times it will be executed can be computed as follows. This one, sigma I equal 1, because we have two basic operation. So here I have two basic operation. So here we have I minus 1 plus minus a plus 1. Here we have 2. So here we have here we replace j equal I plus 1 to n. Here I equal 1 to n minus 1. Okay. So here this is the formula for closest pair. So here we find the two pairs and compare it with the distance. If it is okay, we could value same. If here we have this pattern 2n minus 1 and 1 minus 2 plus 1 equal to n minus 1 to n. Here we have we take n minus 1. Okay. N minus 1 multiply n element of theta n power 2. Okay, here we have 2, that's why. And here I equal 1 to n minus l is n mean I minus, here we have n minus I. So we'll find the n, then we will find the sigma I here. So we'll find this one. Okay. Brute force exhaustive search. Exhaustive search is simply a brute force approach to conventional combinatorial problems. It suggests generating each and every element of problem domain, selecting those that satisfy all the constraints, and then finding the desired element. Example here, the one optimizes some objective function. So here we have mode, generate a list of all potential solutions to the problem in a systematic manner, evaluate potential solution one by one, disqualifying feasible nodes and ones for an optimization problem, keeping track of the best one found so far. When search ends, announce the solution found. Okay, here we have exhaustive search. And here we have applied three important problems: traveling sales problem, livestock problem, and assignment problem. Okay. Before I complete this one, I give you 5 minutes break, and please make the attendance. Okay. So I give you 5 minutes break. class, we study the exhaustive search for traveling salesman. Traveling salesman is we have one point, and we want to visit all the points and return to the starting point. Given in cities with non-distance between each pair, find the shortest tour that pass through all the cities exactly once before returning to the starting city. Alternatively, find shortest Hamiltonian circuit in a weighted connected graph. So here we have all the cost from A to B is to, so maybe I am going to say go like this: A, B, D, C, A. Okay, or I go A, B, D, C. I visit this one time. A, D, C, B, A. So I start with A and go back to A. So here I will see what is the here A, B, C, D, A. So A, B, C, D, A. Here, this is the cost of the link. Here, I place here 2, means here A to B is 2, and B to C is here A to B is 2, B to C is 3. Okay, C to D is 8. C to D is 7. C to D is 7. Then 5. So here 2 plus 3 plus 7 plus 5. Okay. 2 plus 3 plus 7 plus 5. 17. Here we go another option. A, B, D, C, A. So you have 2, 4, 7, 8. 2, 4, 7 is 21. Okay, now here we have A, C, D, A, C, B, D, A. Another one, give me 20. Another one is 21. So we have A, D, B, C, A. A, D, B, C, A. We have A, C, D, B, A. We have here this one. We try to find the cost with the lowest cost. Here optimal is 17 and 17. So here this is the optimal solution. Means the minimum value. The minimum here weighted of a shortest Hamiltonian circuit in weighted connected graph. So here this is the graph, and this is the optimal solution for the traveling assessment problem. Okay, we have knapsack problem. What is knapsack problem? I'll give you an example. If we have a bank, okay, and in this bank there is gold, silver, and bronze, and other materials. And when a thief or robbery comes to this bank, and he has a bag, his bag maybe only can hold 20 kilogram. Okay, so here he want to utilize this 20 kilogram with the maximum value that he can get from this bank. If we have maybe 20 kilogram gold, he will put all the 20 kilogram gold in his bag and go back, run away. So if we have 20 kilogram of gold, if we have only 10 kilogram of gold, okay, he will see, okay, I will take this 10 kilogram of gold. I have extra, I have rest 10 kilogram free. So which I'm going to use, silver or I will go to bronze. Okay, how many silver is available, how many bronze available. So here he is going to utilize his bag. He is going to utilize his bag with the best value that he can get from this bank and with this bag. One thing, we have some knapsack problem. We said 0, 1 knapsack problem, and we have fractional knapsack problem. 0, 1 problem means take the gold, all the gold, or leave the gold. Take all the silver or leave the silver. Take all the bronze or leave the bronze. But this is 0, 1 knapsack. In fractional knapsack, I can get part of gold, part of silver, part of bronze. Okay, this one we call it knapsack, fractional knapsack problem. Here we are going to see the 0, 1 knapsack problem. So here we have weight W1, weight 2, weight N, values V1, V2, Vn, knapsack of capacity W. Find most valuable subset of items that fit into the knapsack. Example, knapsack capacity W is 16. Means the thief or robbery is have his bag is 16 kilo. Now he want to collect the items from here. So item 1, weight 2, value $20. Item 2, weight 5, value $30. Item 3, weight 10, cost $50. The value of this item. Item 4 is $10. Now I want to collect what is the best combination of this one. So if he collect $1, $20. If you collect 2, $30. If collect 3, $50. If collect 4, $10. So still we have here, if 20, we have only 2 kilo, 5 kilo here, 10 kilo here, 5 kilo. Okay, now he will get a combination. If he take 1 and 2 items, 1 and 2 items is 7 kilo. How much he has? He has 16 kilo. 7 kilo, and how much he will get? $50. If he collect 1 and 2 item, he will collect $50. 20 plus 30. If he collect item 1 plus item 3, the weight will be 12, still less than 16, 12, and the value will be 70 USD. So in his bag is 70 USD, and the weight is 12. If he get 1 and 5, 1 and 4, item 1 and 4, it will be 7 kilogram and 20 plus 10, $30. So here, subset 1, 2, 3, 4, total weight here 2, 5, 10, 5, 7, 12, 7. Okay, here we are here in this one, 1 and 4. Now combination between 2 and 3 and 2 and 4. 2 and 3 will be 15 kilo, less than 16. 15 kilo, less than 16. How much he will get? 80 USD. 2 and 3. 2 and item 2 and 4 will be 5 and 5, 10 kilo. How much? 30 plus 10, 40. Now 3 and 4, 10, 15 kilo, 60. Now I will combine three items. Let me try 1, 2, 3. 1, 2, 3 will be 17 kilo. 17 kilo, 17 kilo, I cannot, not feasible. Why? Because we have, he can only, his bag can only get 16. And now we have, if I collect item 1 and 2 and 3, he will get 17 kilogram, which is more than his bag. Okay, so not feasible. Now I will collect 1, 2, 4. 1, 2, 4. How much also? 12, 5, 17. So it is not feasible. Okay, 1, 2, 4. 1, 1, 2, 4, 2, 5, 5. How much kilo? 12 kilo. How much the 12 is okay, feasible. But how much the total value will be 20 plus 30, 50 plus 10, 60. I will try 1 and 3 and 4, and this one 60. 1, 3, 4, 2, 10, 15, not feasible. Because we have 2 plus 10, here item 1 and item 3 and 4, we'll have 2, 10, 12, 5, 17. 17 not feasible. We have only 16 kilogram. 2, 3, 4, 20 kilogram. Not feasible. Here we have 5, 10, 5. 20 kilogram not feasible. Now 1, 2, 3, 4. 1, 2, 3, 4 is 22 kilogram, is not feasible. So what is the optimal solution for a knapsack problem using brute force or exercise is 80 USD. 80 USD. Now we have something called exhaustive search assignment problem. Here there are n people who need to be assigned n jobs, 1 person per job. The cost of assigning person I to job J is Cij. Find assignment that minimizes the total cost. So here we have this solution. We have this is the assignment. This is the matrix. We have person 1. If he do job 1, okay, he will take $9 to finish this job. If person 1 do job 2, it will take $2. If he take a job 3, he will do the 3. He will take 7 USD. Job 4, $8. Like this here, we fill person 4. He take for job 1 $7. For job 2 $6. For job 3 $9. For job 4 $4. Here we have. You want to see what is the maximum, what is the best. We need to minimize the total cost. If I get job 1 to person 1, job 2 to person 2, job 3 to person 3, job 4 to person 4, how much will be? 9 plus 4 plus 1, 5, 9 plus 9, 18. This one will be 18. If I say 1, 2, 3, 4. If I say here 1, 2, and here 4, 4 will be for job 3 will be person 4, and 3 will be here how much? 30. In the here, job person 1, job 1, person 2, job 2, person 3, job 4, person 3, job 4, person 3, job 3, person 3, job, person 4, job, person 3, job 4, person 3, job 4, and person 4, job 3. So here we have 9, 4, 8, 9. 9, 4, 8, 9. The total is 30. We need to find the minimum value. So here we compare this one here where I distribute this job to job 1 or job 2 to person 1, person 2. So in each, we have to assign at least one job to one person, at least one job to one person. Here we have one job to one person. If we have some additional information, maybe a person one can do a lot of jobs. This is different scenario. But here, one person, one job. There will be a total of 24 different assignments, 4 to permutation. The smallest total cost will be the optimal value. Okay. Any questions so far? I think it's easy. Okay. Any questions so far?
No question, Doctor.
Okay. Now I think it is here. It's easy this one, but we add this for salesman, and we have for the knapsack problem, and we have for the assignment problem. This is the three problems that we didn't discuss last week in our class. Okay. We complete brute force design strategy part 2. A brute force is solution to problems involving search for an element with a special property, usually among combinatorial subjects such as permutations, combinations, or subset of a set. Method generate a list of all potential solutions to the problem in a systematic manner. Okay, evaluate potential solution one by one. This qualifying any feasible one and for an optimization problem, keeping track of the best one found so far. When search funds announce the solution found. Exhaustive search travel CSC problem. We say this. We call it a Hamiltonian circuit. Okay, we did this example. So in layman's terms, Ayman's terms, the problem asks to find the shortest tour through a given set of entities that visit each city exactly once before returning to the city where it started. The problem can be conventionally modeled by a weighted graph with the graph weights representing the cities and the edge weight specifying the distances. Then the problem can be stated as the problem of finding the shortest Hamiltonian circuit of the graph. A Hamiltonian circuit is defined as a cycle that passes through all the vertices of the graph exactly once time. So here it is named after the Irish mathematician Sir William Rowan Hamilton, who became illustrated in such cycles as application in his algebraic discoveries. So we did here, we have one multiple cities. I want to visit all the cities and return back to the main city that I have started with. Okay. Given n cities with non-distance between each pair, find the shortest tour path through all cities exactly once before returning to the starting city. Alternatively, find shortest Hamiltonian circuit in weighted connected graph. So here we have this example. Okay, what is the solution? We did here solution on the previous slide. Here we have A, B, C, D, D. Here we have A, C, D, B, A. Here we have A, B, D, C, D, A. Here we have A, B, D, C, A. So multiple options, and we have weight for each transition from one city to city. We have weight, and we have add this weight to the solution and check that the answer. Okay. So this is the solution. Here we have A, B, C, D, A. Here we have, this is the cost. So here the minimum is 1770, means go from A to D to C to B, then A. This is this solution, or go A, here A, B, B, C, here A, B, C, D, A. So this give me 17. Knapsack problem that we discussed now, the knapsack problem with weighted and values, and here, and we get this subsets, and we have total weight, and we check for the most feasible with most value. Okay, the assignment problem that can be solved by exhaustive search. Here, the assignment problem, we have n jobs and we have n persons. Each person has one job. Consider on people who need to be assigned to execute jobs, one person per job. That is, each person is assigned to exactly one job, and each job is assigned to exactly one person. The cost that would occurrence if the eighth person is assigned to the J job is as non-quantity Cj for each pair I want to n. For I and j, for each pair I, pair j, 1 to n. The problem is to find assignment with the minimum total cost. So here we have this matrix: job 0, job 1, job 2, job 3. Here the cost, here we have, there are people who need to assign in jobs, one person per job. The cost assigned person I to job J is Cij. Find the an assignment that minimizes the total cost. Okay. We need here total, the minimum size of total cost. So algorithm generate all legitimate assignments, compute their and select the cheapest one. How many assignments there? So here this is the total cost. How many? Here we have 24 combination. For this particular research, the optimal assignment can be found by exploiting the specific feature of the number given. For final comments on exhaustive search algorithm run a realistic amount of time only on very small instances. So here, if we have small instances, we use maybe using exhaustive search, or we call it brute force. In some cases, there are some better alternatives: Euler circuits, shortest path, minimum spanning tree, signing problem. In many cases, exhaustive search or its variation is the only known way to get exact solution. Okay, here we finish these slides and we compare with the here I give you an exercise to solve it. I give you exercise. Okay, let me share the question that I write you. I'll give you 10 minutes to solve this question using knapsack problem. Give me the best bag can take only 50 kilogram. Please solve this one. I'll give you 10 minutes to solve this one. So, Assalamu alaikum wa rahmatullahi wa barakatuh. So, who solved the question? Who solved the question? What is the best combination? Hello? Who solved the question?
Doctor, may I try?
Okay, Ashraf. I will stop sharing. Share your answer.
All right, wait. Funny.
You have to mention all the possibilities. All the possibilities. Okay. Gold, silver, bronze, 50, 30, 35, iron, 60. Or gold with silver is how many kilogram? 30 kilogram. And the total cost is 50 plus 30, 80. Am I right?
I guess.
80. Here, gold, bronze, gold, bronze. Here we have 10.
What?
And we have bronze 30, 40 kilo. So am I right? 40 kilo. And here, here will be 85. 50 plus 35, 85. So here we have gold with iron will be 60 kilo, not feasible. Silver with bronze, silver 20 kilo, bronze 30, 50 will be 60, 50, 65. Okay. Now here, silver with iron, silver 20, iron 50. 70 kilo is not feasible. Silver with bronze with iron will be also not feasible because iron is already 50 kilo. Anything with iron will be not feasible. So here will be, this is the best is 85 kilo gold bronze. Who get this answer? Thank you, Ashraf. This is the answer. So here, when you need to answer a question like this is the best solution. We mention all the possibilities, and then we select the best solution. This one exhaustive search, brute force, using brute force to solve knapsack problem. Okay, clear so far? So you can share the answer with your friends, Ashraf. You can share. Can you share the answer with your classmate how to solve this one?
Okay.
Okay. So share the make the question and make the question this question. Make the question with the answer in one sheet and send to me also. Make this question in one sheet with the answer and send it to me also, and I will share it with the group of lab of your group, lab A. Group A. Group C. You are group C, am I right? Group C and Group D. You share it with Group C, this answer. So please here make the answer here and please send it to me. Okay, any questions so far? Any questions so far? How we get the solution? It is easy. It's easy when you understand how to deal with the algorithms, and this is the core subject in your in computer science. When you know how this is working, you will solve all the questions, inshallah. So please please don't forget to make the attendance online. If there is no question, you can leave today early. We can stop here for today. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.
Thank you, Doctor.
Ashraf, don't forget to send me the answer with the question. Okay?
Alright, Doctor. Thank you, Doctor.
Okay. Thank you very much. Okay. Terima kasih. Jumpa lagi. We have